All right, so this morning we're going to be talking about how to use DTRACE for reverse engineering. We got a lot of stuff to go through, so we'd like to get started right now. We're going to move kind of fast through the intro, basically introduce DTRACE, how we can apply it to reverse engineering, and then talk about some of the specific examples we've done. So let's give you some background. DTRACE was originally created by a couple engineers at Sun Microsystems back in 2003. It was originally released in Solaris 10 in about 2005 and open sourced under Sun's CDDL license. So since then, and just recently in October 2007, it was included in Apple's OS X Leopard. So they went ahead and ported it to OS X. There's been some work to port it to FreeBSD. A partial implementation is out for QNX, so it's kind of spreading its ground. There's some licensing issues, between CDDL and the GPL and stuff, but aside for that, support is expanding. So to give you a basic overview of what it's doing, DTRACE basically lets you trace an application at runtime. It lets you observe what the application is doing at runtime. So the way that this works is that you set probes, which are kind of like hooks, specific points of condition that you want to instrument. So you define the places you're interested in, and you define the action that you want to take, which usually is in the form of some sort of measurement or comparison or recording. So here's the basic architecture. Let me get my laser pointer.
That thing's like a lightsaber.
I know, right? So let's start at the bottom here. These are different categories of probes. They call these providers. So for instance, here is the FBT, is a function bounding tracing. So this is an area within the kernel that lets you trace kernel functions. There's also a syscall provider. There's a PID provider. So each of these categories of probes are pretty different. We're going to focus mostly on syscall and PID providers. So these are all built in the kernel, and so there's the DTRACE environment within the kernel, and then the DTRACE sort of interface of the kernel, and then there's this libdtrace, which a number of things interface with. Different system utilities use the libdtrace userland library. What we're most interested in here are these scripts up here. We're going to be writing our own DTRACE scripts and then feeding them into the DTRACE application. So let's talk a little bit about the D language. D is advertised as being a subset of C. Now, this language is something specific that the authors created for the purpose of DTRACE. So you write the C language, which then gets compiled and checked for safety in the intermediate form. Because we're dealing with code that gets run in the kernel, it needs to be safe, so that the safe checking happens at runtime. If you write code that accesses invalid memory, the DTRACE environment is going to deal with it rather than having it affect the application. Now, although it's a subset of C, one of the major differences is that you don't have control flow. There's no loops. So that'll really throw you off if you're expecting to see a standard, your standard type of programming languages. Now, there's good reasons for that, because you don't want to be, if you're the kernel, you don't want to be handing off control to some user script that has an infinite loop in it, because you're never going to get control back, and it's going to totally hose the system. So there's a lot of safety and performance goals taken into consideration when designing DTRACE.
DTRACE is primarily designed as a real-time debugging tool that you can walk into. Say a Sun consultant can walk into any system running Solaris in real time, a live system running a web server or something, and do some transient debugging safely without ever having to worry about the system going down. That's sort of a paradigm shift, because in the past, if you wanted to hook up, say, a kernel debugger or a user mode debugger, you'd have to have a parallel system to your live system configured exactly the same. That would allow you to debug what you're expecting to see on the server. So DTRACE has completely made that possible for debugging live systems.
Okay, so the D language itself looks a lot like awk, if you've ever seen that. So it's kind of block-based, and you have these predicates that are conditions. So in awk, you're doing something like processing the input of a file. So you look at one line and you say, does it match this pattern? If so, let's go ahead and perform these actions. Does it match this other different pattern? If so, let's perform something else. So the D scripts have the same structure. There's this thing called a predicate, which is a conditionary logical statement. So if it's evaluated to true, then the actions that you specify occur, the recording and such.
So predicates are often like arguments to functions, that type of stuff.
Yeah, you can
files access, syscalls.
Record timing, record parameter values. Okay, so the bottom line for performance is that, like David was saying with the Sun engineers going into production environments and trying to debug things, performance and safety is a major concern. You don't want to be adversely affecting a live production environment. So that was one of the primary goals. Bottom line, it's very efficient at what it does. But even with that taken into consideration, you have to be careful when tracing. You can't go tracing everything, otherwise things get really slow. All right, so there's a million things you can do with DTRACE, and you'll be familiar with some of the applications of it from things like TRUS and ptrace, where you're tracing applications in real time. But what DTRACE is doing that's different is it gives you the functionality to specify what it is you want to observe in the runtime environment and how to deal with it. So the real key takeaway here is that DTRACE combines system performance analysis, debugging information, and execution analysis into one tight package. So it's the Swiss Army knife for us reverse engineers. It allows us to kind of easily gain a general understanding of what an application is doing, or to get very specific and analyze a specific situation within an application. So as a reverse engineer, this is exactly what we want to do. We take an application, we understand what it's doing in a broad sense, and we want to pinpoint a specific situation.
One of the important notes there is that, let's go back a slide, the idea of transient processes. If you have GDB, you're essentially debugging you're using one userland process to debug another. If something's happening in the kernel, you really have no visibility. As soon as a call's made in the kernel, you have no idea what's going on. With DTRACE, sky's the limit. It's the all-seeing eye on the system. You can go ahead and switch from a userland application and say, when it does something in the kernel, just follow it up in there and show me what it's doing. So there's really nothing that's off limits for a single D script.
Okay, so let's give some examples here. Some things you're going to want to do is like things like monitor I/O time, the syscall stacks at particular times, monitor the network or maybe what files are being opened by different processes. There's a toolkit out there called the DTRACE toolkit, which has a ton of really good examples of things that have already been implemented over, DTRACE has been out for a number of years now, so it's pretty comprehensive. So if you're interested in learning how to write your own DTRACE scripts, that's the first thing you should do, is go check out what's already been done in that toolkit. Chances are you're going to find what you need there. On OS X, there's also a GUI called Instrument, which is part of the developer tools. It's a flashy graphing program that lets you specify what you want to trace and then graphs it out. So they have some canned examples for tracing memory leaks and I/O. And
it's really just a front end to DTRACE aggregation. So it is useful in the sense that you can right away get some useful things without having to know much about how DTRACE works. One of the cool things is that they actually allow you to write a DTRACE script and then use the visualization front end without having to worry about writing your own OpenGL or something like that.
Okay, so let's look at a couple examples. This is a small DTRACE script. You can see it's one line right there. So with the provider syscall, we're tracing syscalls, all syscalls entry point, and we're just going to count the number of times that each application has executed a syscall. So this is the result here. You can see VMware VMX has got almost 7,000 syscalls. So from here we're able to see what's going on across the whole system, what's using the most resources. So typically what you'd want to do from here is say, something's going on with VMware. Let me dig down deeper. Let me trace only VMware and monitor which system calls it's making so I can figure out what it's doing most of the time.
The other cool thing to note here is that we didn't have to do any printf formatting or anything to get it to look like that. That @ sign represents an aggregation, which is like sort of a formatting style to the standard out. So that's really like implementing not ptrace, but like ltrace or truss in a single line, which is pretty cool.
Okay, so another example. This one will monitor across the whole system all files that are being opened. So we're monitoring all open calls, open syscalls. And all we're going to do is print out the name of the executable along with the file that was opened. So here's the output from that. You can see that on the left there's various applications that are running and what files they're opening. So iChat's opening a plist configuration file. VMware is accessing dev random. So this would be interesting if you're trying to trace an application that's maybe suspected malware. You want to see what it's touching on your file system. Okay, so now that we've gone over DTRACE a little bit, let's talk about some of the lingo. Basically, you've got a provider, which is that category of probe. It defines the way the probes behave. Then you've got your probe definition, which is split into 4 parts. Provider, usually the library, the executable name, a function name, and then the last field is either entry or return or blank. So you want to instrument the entry point of the function, the return point, or every instruction in between. Then after that, you specify the actions. So here's the generic form of a D structure, of a D script. You've got the probe, which comes in those 4 parts. The predicate is some optional condition under which you want to execute these actions, such as printf, print the stack trace, make some calculations.
All right, so let's get to the good stuff. We've given you a little overview there. So DTRACE is really useful for understanding how an application interacts with the rest of the system through function calls, system calls, I/O, networking. Like I said, it's really cool because it's like a glue. It's an integration that allows you to do things that normally would take, half a dozen tools to do. You could have a kernel debugger, GDB, LTRACE, STRACE, all in a single D script, which is really cool. It's built in as a hook, so it allows you to hook in an application or monitor what you want. The way I see it is it's almost like a friendly programmable rootkit. It's this all-seeing eye in the kernel that just will allow you to take a look at anything you want. It's got hooks into everything across the entire system. And what's nice is that as application developers realize the power of DTRACE, more and more applications are getting these native DTRACE hooks. For example, Firefox, MySQL are really cool. You have hooks into the JavaScript, so you can actually look at what the JavaScript function arguments are in a browser-based application from DTRACE. So there's a lot of specialized tools that would normally be required to do this stuff, as I said before, which we can do in a simple DTRACE script. So one of the important things I want you to take away is that DTRACE is not a debugger, right? Debuggers work by using 3 instructions to pause at certain address spaces, and DTRACE doesn't do that. It allows the application to continue as it would normally, and it just kind of comes in there and steals the information that you need at the time you specify. So don't limit yourself to thinking of probes just as breakpoints. The way we like to think of DTRACE is as a rapid development framework for RE tasks. So we actually proved this just the other night. Our buddies Nate and they did a URI presentation yesterday, if you saw, and they actually found a really cool flaw in iPhoto. So when we got here to Black Hat, they left us a message and said, hey, it would be great if we could hook up with you guys and see what you did as far as OS X. So in just a couple hours at the bar the other night, we got pretty far and almost developing an entire exploit. So that was really cool for us because it really validated the idea that, hey, this is a very quick way of getting a general idea of how a vulnerability works. This was in a printf statement, so we were quickly able to see what the format string bug was, and we'll demonstrate more of that capability later. So we think of it as one of the greatest assets is speed. So as he showed you before, you can do complex operations with a single line. So DTRACE gives us a lot of really cool features for free: control flow indicators, symbol resolution.
We can quickly print the call stack trace, look at CPU registers, function arguments, and we can do all this both in the kernel space and in the process space. So that's kind of one of the key points about DTRACE is its visibility. Most tools are not able to trace kernels. So let's look at some of the helpful examples we get, some helpful features of DTRACE we get when it comes to reverse engineering. So this graph shows the control flow indentation. So we can quickly just trace function entry and return points and get an idea of the behavior of the application, which functions are calling which functions, what place of the code we're at, We also get symbol resolution there. So in this graph, it's showing basically the library and the function name that's being called. We'll get into other ways of graphing out that data in a more visual way too. So here's a UStack example. This is in an FTP server. In this example, we trace the strcmp function. You can see at the very top. So we get a sense of the call stack trace, not only which functions are being called, but the particular offset in the function. So we can pinpoint the exact instruction.
Yeah, a good point here would that to be, GDB gives you perfectly fine capability for printing a stack trace at a breakpoint. But if you've ever went through and said, I want to see the stack trace every time a breakpoint is hit, this will just allow the whole thing to run and record all the stack traces at every printf function. So it has a lot of capability beyond just what GDB stack trace provides.
So here's an example of recording the argument to a function. So imagine that the probe is tracing the entry point of the function. We're just going to print out the first argument. So the example output at the bottom there shows the strcmp function, and the first argument is special_1. So this is exactly what we were doing with Nate and Rob's example the other night with the printf, is that we wanted to, printf is called a zillion times in the application, right? Most of the time we're not interested in it, but under a certain case it's processing the user input and there's memory corruption. So what we were able to do is figure out what the argument was in that particular instance. So we could trace up to that point, pause the application, and then proceed with analysis, like dumping the memory and trying to find where our input was in the process memory space.
One of the cooler things we did there is, DTRACE isn't a scalpel. It's not normally, it doesn't allow destructive actions. It doesn't allow you to change the values of registers, things like that. So what we're able to do is trace to the point we're interested in, and then just say transfer control to GDB, and then GDB does what it does best, which is go in and change memory and look at those applications. So we're able to combine the power of both, and it really works in a nice symbiotic relationship.
We can also, here we're using copy out to get the values. We can also copy in values. So that would be a destructive action to change the memory of the application. So we can also print out the CP registers at any time. We're often interested in the value of EIP or the next instruction to execute.
Yeah, but you can't modify the registers. You can modify memory values, just not registers.
So here's a destructive example. This one's kind of cute. What it's saying is that we're instrumenting the syscall called uname, the entry point, and then it records where in memory the first argument is, which is a buffer, and then at return from that function it copies all this data in here. So if you're familiar, uname is a command you often execute on this Unix command line, which will print out, the operating system version and the kernel version and the architecture you're running on. So this destructive action will change that value. So if you go run uname, this will change to print out that you're running Windows on a PowerPC in 2010.
Now, if you're familiar with rootkits, that would actually be a significant challenge in a rootkit, right? You'd have to load a kernel module, you'd have to hook into the kernel function pointer table and redirect execution into what you want to do and re-output it. We're doing the same operation that was so complex in 5 or 6 lines of an interpreted D script. It's amazing.
Okay, so here's another example of snooping. In this particular example, we want to capture what any other application is writing to the standard output. So by using this script, I can watch what David's typing and what his terminal's printing out to him. So it sounds like a keystroke logger or something. So hopefully this gives you some good ideas about how to apply this to reverse engineering. You can monitor the stack, so naturally we could pinpoint stack overflows. We're also going to talk about code coverage and how you could use code coverage as a metric for fuzzer feedback. Heap overflow monitoring, and even implementing, basic HIDs. So
the big takeaway here is don't think of DTRACE as a debugger. They can work together, but they really have 2 separate functions. So I'll talk about some of the differences for when you're using it as a reverse engineering tool. DTRACE can instrument both the kernel and userland applications at the same time. That is an incredible feature. I don't know how many, I've actually done and went through the pain of attaching a kernel debugger at the same time I had GDB on a process. So if you've ever done that, you know what I'm talking about, and it is a painful experience. With DTRACE, you don't even think twice about it. The kernel is your playground. It's not a problem at all. one of the problems with debuggers is what it's great at doing is it replaces your breakpoint right within 3 pause instructions. That's cool, but when you're dealing with multi-threaded applications that are really time and thread specific, a lot of times that can cause you problems. You get all these phantom exceptions. I don't know how many of you out there have been writing an exploit. It worked great in the debugger, and then you switch off to normal, and it completely doesn't work because the memory layout's changed, execution has been sort of screwed up. With DTRACE, you don't have those problems. Normally, if you write a DTRACE script and you're setting up an exploit based on the information provided there, it's going to be exactly the same as if the application wasn't under test. So that's because DTRACE actually copies userland memory into the kernel first and then allows you to write reports or carry out actions based on that. So the way I'll use a little Dr. Phil analogy here. The way I like to think of DTRACE is a glue in a greater reverse engineering type of integrated development environment. So IDA Pro is kind of your X-ray, GDB is your scalpel, and DTRACE is your stethoscope that's going to allow you to listen to something in real time. So as I said before, traditional debuggers, they can do some funky things in memory layout. So if you're having a problem with that, DTRACE is great for that. There's a few downsides to DTRACE. Obviously, it's not a panacea. It doesn't have exception handling. So if you're trying to monitor a fuzzer and say, hey, when I want a first chance exception, I want to know what's going on, see if I have a flaw there, you're not really going to be able to explicitly do that with DTRACE. The other problem is that there's quite a few ways to mess with DTRACE. Things like jump tables, code obfuscation, they have the same problems as GDB or other things like that would have. Currently, there's not a ton of anti-debugging code out there that specifically targets DTRACE, so there's no API that just says, is DTRACE present, kind of like you would do on a Windows machine. But Apple, in their infinite wisdom, decided that might be a good idea to go ahead and implement that so people could prevent you from reverse engineering applications. So they did implement a flag called PT attach deny, which we'll show you later is completely trivial to bypass. Of course, with the name DTRACE, the first thing you're going to do is make a comparison to conventional debuggers that are conventional tracers you already know, like strace, ltrace, ktrace, etc. DTRACE is not quite the same. So the way trust or something like that works is it sends control messages to procfs that will tell procfs to pause when a syscall happens so you can print out. Now, the problem with that is that it really affects performance. So Brendan Gregg, one of the guys who's the primary authors of the DTRACE toolkit, he compared what DTRACE does in monitoring system calls to what, say, Trust does, and he found that Trust had a 64% negative impact on any applications under test or under trace, while DTRACE has about 0.3% impact. So you can see that the performance increases there, which allows the application to behave as it would normally, and it doesn't feel like it's an application under test. Valgrind is a very cool tool. It's not very extensible, and it requires quite a bit time to set up. So DTRACE is not quite the same. You can write a simple script really quickly to trace the instructions you're interested in without 2 hours of setup time. And we all know reverse engineers are pretty lazy guys, so the faster the better. The easier it is, the more likely you're going to go out and look for bugs with it. So again, the D language also, we talked about this before, there's quite a bit of limitation there. It mostly prints stuff to the standard out. There's a lack of loops, but we have a solution for this, and we address these limitations by interfacing with Ruby. So we're going to get into our actual toolkit that we developed based on this. After looking at the power of DTRACE, but looking at some of the shortcomings and saying, how can we address these for reverse engineers, we came up with this toolkit called retrace. So what's cool about Ruby DTRACE is that when you combine it with the power of Ruby, you have the best of both worlds. You have a strong object-oriented interpreted language, and you also have the power of DTRACE, which is really cool. So we base this on top of Chris Andrews' libdtrace binding. So he wrote Ruby bindings to the actual user land libdtrace library. So what this gives us is, as I said before, great object-oriented programming. So we can create tracer objects that would provide a really powerful high-level API for people interested in reverse engineering tasks. We can do iteration. Wow, imagine that. We have a loop and a lot of those other things. One of the best aspects of this, of using Ruby, is that we can leverage the existing Ruby-based reverse engineering frameworks like Metasploit, IDA-Rub, librub, meta-ASM, all of that great stuff. So this puts it in a class of similar to programmatic debuggers like PyDBG, NoxDBG, and Immunity's great debugger. So what we're going to talk about a little bit is IDA-Rub. It's actually wrapping to the IDA SDK. So what this gives us is the power of IDA's disassembly combined with our real-time trace analysis. So what we're going to show you in a little bit is that we're able to trace an application and have it write comments or color an IDA disassembly. So what's great is you're going along and you're doing your static disassembly and your static analysis of a binary. And you're saying, I wonder what this does in real time. So you write up a short retrace script, and you can comment up or set values for anything in your disassembly. So they really work great together. And that was created by SpoonM, who's part of the Metasploit developer team. So we find in general that our vulnerability analysis times and our exploit development times have been greatly reduced due to the power of this retrace framework. We were just talking to Nate and Rob the other night about how GDB is a great tool, but it's getting kind of long in the tooth, and there's a lot of things it can't do. So on the Win32 platform, you got great stuff out there like IDA, Ollie, Immunity Debugger. It's really lacking on the Mac side. And of course, this works, all the stuff we develop also works on any system that can run Ruby and DTRACE, so Solaris, etc. And for exploit development, because you can track your data flow through the entire application really trivially, it really helps quickly with those hard to solve problems of where the heck's my shell code, where did it go, what are some function pointers I can overwrite, etc. So DTRACE, as we said before, it hooks every function in a process, so we can trace execution based on what functions are run. So when you're talking about instrumenting a fuzzer with code coverage, how many of you out here use PyMay or something like that? So what PyMay does is it does block-based code coverage, where every set of instructions that has to be run together is considered a basic block. So your average really complicated application would have something like 60, 80,000 blocks in it. What we can do that with DTRACE by just saying, hey, IDA, give me your basic block information, and we'll set trace points in DTRACE and do stuff like that. But we find it useful for just a quick code coverage analysis. Hey, I think there's a bug here. Let me see what functions this fuzzer is going to hit. So it's really great for that, and it writes the colors right back into IDA, which we'll show you a little bit later.
All right, so let's talk about monitoring the stack. So what we're going to be doing here is looking for a classic buffer overflow on the stack. The reason we're interested in this is that once we find the buffer overflow, we have to pinpoint the exact condition it's happening under. So we want to know which function's vulnerable. We want to know how we got there. We might want to stop the application, proceed with analysis with a debugger, or when we detect this overflow, we may want to send a signal to our fuzzer saying, hey, save that last output you just did because you found a buffer overflow. You might want to even act as a HIDS, like let's just stop the application and kill it because a buffer overflow is about to happen. We're about to have a memory corruption. So here it is, one line, right? This is kind of a cute trivial example, but we're instrumenting every function, every return value, and we're just checking EIP, the next instruction to execute. So and when you're testing, you often use a string of A's or 414141 to overwrite a bunch of memory. So if our next instruction to execute is ever that value, we're going to say, hey, don't tase me, bro, and stop the application and proceed with analysis.
So before we mention one of the limitations for DTRACE, like when you're running a fuzzer, is that exception handling is not generic. But in this case, a lot of times you're interested in a specific exception. So what we're using here is basically a predicate to say, if this ever happens, there's an exception. And I find that that's actually to your advantage rather than generic standard exceptions.
Okay, that's nice, but what we really want is a more generic overflow detector that regardless of the value of EIP is going to be, we'll say, hey, I was supposed to return to this address in memory and I'm going somewhere else. So let's talk about implementing that. When we try and do that, we have to be aware of some of the problems that DTRACE has. By design, it's meant to be efficient, so it keeps these buffers where it queues up probes and stuff. And if it if the buffer fills, it'll just drop those probes. So you have to hone in on exactly what it is you want to trace so you don't have that situation. You can also adjust the size of the buffers and the frequency at which buffers switch. There's a lot of DTRACE specific options you can tune to better your chances. So our basic approach here is to store the return value on function entry point. So the idea is that you enter a function and there's a new stack frame on the stack. You return from that function and it pops off that stack frame and returns to the previous one. So you store the next instruction in each frame that's in the program that you want to execute. So during a buffer overflow, that next instruction to execute in the stack gets overwritten. So that'll happen when, so what we'll notice is that we pop off that stack and the return value is not what it originally was. So the first approach is to, on function return point, check if the stored value is different than the next instruction to execute. But there's a few problems with that. The compilers will make things called tail call optimizations, and that'll screw up the basic assumption that each function call creates a new stack frame. You just have to be aware of how DTRACE handles that. There's also functions that DTRACE can't trace. Like David was saying, when you have jump tables in line with the program text, DTRACE will go like, whoa, I don't know what's going on here. I'm going to trace the entry point, but there's no return probe for this function. So that'll really throw off anything you're trying to trace where you want to know the entry and return points.
So what was cool about this is one of the first things that we actually got into when we were evaluating DTRACE as a reverse engineering framework. We're big fans of PyDebugger, and Pedro Mamini actually made a really cool script called Stack Smash Detector that really uses the same technique. So we're saying if we can get DTRACE to do a similar thing, we're in business here, and we've pretty much validated our idea of using this for reverse engineering.
Okay, so the tail calls, this is actually painfully boring, so I'm not going to go over the details too much. If you're interested, please stop by. I'd love to talk about it. You just have to kind of note how DTRACE deals with tail calls. Since there's not a new stack allocation and you're calling a new function that's reusing that stack frame, DTRACE reports it as an extra entry in return and blah, blah, blah. So once you know how it works, then you can account for that in your DTRACE script. So our new approach is to store the return value, store the address of the return value, and then at function return point, we're going to look up that value again. So we're never checking the next instruction. We never check EIP. We just want to know if the value on the stack ever changed. Now, we have to deal with missing return probes somehow. Basically, our only option is to exclude them from the trace entirely. So how can we detect them? DTRACE can report to you a list of all probes it knows about. So this is easy. You just say print all the entry probes, print all the return probes, find the differences, and exclude those with a predicate like there at the bottom. The probe function name is not equal to the function name. All right, so let's show the Stack Overflow in action. So there's a little video here we prepared. So down at the bottom, I'm going to start public available RTSP exploit. I think this came out about a month and a half ago or so. So it's running on the local host. Up here, I'm going to start QuickTime. This is the application we're going to exploit. So I'll fire it up and then connect it to the exploit server. The payload's delivered, and you're expected to see the program crash. So first, what I'll do is start up our retrace toolkit. So this is this is kind of like our environment with it. It combines the Ruby with the DTRACE. So we got a number of helper functions. So I'll activate the stack monitor on the QuickTime process. You can see it instrumented 21,000 probes right there. So now we're going to go back and activate the exploit in the application. So we open the URL, connect to the local host, and you'll see the payload was delivered right down there, and there was a bunch of stuff printed. The application here is now paused. DTRACE stopped it. So the buffer overflow hasn't, it's occurred, but the return pointer hasn't been executed. So you can see the first message there, stack overflow detected. So here's the cool part. We pinpoint the exact situation. We know the library, QuickTime streaming. We know the exact function name. We know what the return value is supposed to be and what it actually was.
You don't want dead beef as your return value.
Here's the CPU registers. This gives you an indication of what you control. EIP in this case, this exploit controls almost all of them. EBX, EDI, ESI, and so on. Here's another really valuable thing. We get the stack trace with symbol resolution and the offsets for each function. So we can go track down the exact function, the exact instruction that was executed within that function. So from here, you'd want to proceed to dump the memory of the process, search through that memory, looking for your shellcode or other input, or just say, hey, what's around my input? Because maybe I'm interested in overflowing that. In this case, we don't want to violate Apple's EULA, so we're just going to kill the process and show those steps with another application.
Remember, kids, it's illegal to attach a debugger to QuickTime.
If you were to do that, you'd actually be able to look at the call stack and see a nice no-op slide and stuff. I mean, I'm sure. So what we're going to do here is look up ADM. It's a common chat application for OS X. We'll dump all the memory from that. So we stop the process so it's paused, dump all the memory, and then we can search through the memory for either shellcode values or specific strings. In this case, we're going to look for bin bash. Say we're interested in doing a classic libc attack. We'll want to know some address in the process's memory space we can use as a parameter to.
So this is not actually part of DTRACE. We had to write these as helper functions to help to come up with work around some of the limitations of DTRACE.
Right, the memory dumping and searching aspect is done in C and Ruby. So these are my memory addresses here.
Each of those contains a string / bin bash.
So here I'll attach a debugger. I've recorded those addresses here just for later reference. Here is the stack trace, what it looks like in GDB. You can see it doesn't have the instruction offsets. This is the command to print out the contents of memory. So as a string,
there's our bin bash.
But in this case, there's a whole bunch of other crap that we're not interested in. We couldn't use that for our return to libc attack. But the rest of these values, they all contain bin bash followed by the null terminating sign. So we could use any of those parameters. So from here, what you'd be interested in doing is redoing the exploit and seeing, are these addresses static? Do they always appear in the same locations in the process as memory?
Remember, with Leopard, you've got to deal with ASLR. So to really write a functional stack exploit, you actually have to have some functionality like this. And we couldn't find anything publicly available, so we just had to write our own.
Okay, so that's that. Some advanced tracing topics is instruction-level tracing. You actually instrument every instruction in an application. Now that's going to kind of slow things down, but you just properly scope stuff and it'll work out. So once you instrument every function, you can print out the IP, represent that in IDA, and then visually see what's going on. You can also print every instruction to give your fuzzer some idea of how much code you're covering. You could use this as code coverage metrics. All right, so code coverage. The approach here is simple. There's a lot of code coverage tools out there. What you want to do is print out the instruction that's being executed and then feed it into IDA-RUB or just record it in the trace. So this will let you do, once we get that list, we can just feed it into IDA-RUB and harness the power of IDA's static disassembly.
Harness it.
Right. So we color things in red. We'll get a screenshot of that in a minute. So you can do this in real time. You can actually watch what's being executed in IDA in real time, except that naturally it goes super fast, so you probably won't be able to tell. Okay, so this is actually really easy. Here's your probe. This is all you got to do to print out the next instruction. So you're tracing a particular process. This is the module within the process, every function, and we don't trace entry return, just every instruction.
So again, this is a lot faster than most code coverage tools out there that are, like PyMate. They're going to require significant setup time. This isn't quite as robust, but again, we're lazy, so we like the quick fix.
So we do is print the instruction, then we'll use Ruby DTRACE to get that information. Then we'll use IDA-RUB to talk to IDA, which has its own IDA-RUB plugin. and then draw the colors in the disassembly.
Remember, you don't actually have a sophisticated GUI for IDA on the OS X side. So the whole time in our normal workflow, we're working on Solaris or on OS X, and we're running IDA in a virtual machine and connecting to it over the network. That sounds a little complicated, but really when you use like Unity mode in something like VMware Fusion, IDA just looks like a window, just exactly as it does in Windows, and you're using it just like it's any other application on your system, so it's pretty cool.
So this would allow us to get traces for, say, particular code sessions you're running. Let me move on here. Here's code coverage visualization. So this is what it looks like. If you're interested in pinpointing a vulnerability in this function, you want to look at these red blocks. You don't care about these because they never executed. So just hit. So the red is what was covered. Here's another example of illustrating a call graph. So this gives you a view of what's happening at runtime. So IDA is giving you the static analysis. This is the runtime analysis.
This is really useful for like malware analysis or anything you need to understand at a high level how it's working, what function it's calling.
So this is just a shrunk down version of this. But it gives you a big call graph. These will be huge, like 3,000 or like giant, I don't know, I forget the pixel resolution, but like 3,000 pixels wide.
So I don't know how many of you are familiar with GraphViz, but you know, basically you just format your printf and GraphViz takes care of the graphing for you. So we've seen stack, we've seen code coverage. Let's talk about the heap. So most of the new attack vectors out there are based on heap exploits, right? People are doing a really good job with non-executable stacks, stack canaries, etc. So most of the common exploits or the reliable exploits out there are moving towards the heap. So things like unlink write4 primitives on Windows or Vista, stuff like that are almost extinct. So if you want to learn more about that, I recommend an excellent paper by Dave Otto and Nicholas Wassman called Debugging with the Immunity Debugger. They talk a lot about heap determinism and how that's useful. So what you're really interested in when you're trying to exploit heap vulnerability reliability is you're looking at the allocation patterns. You want to massage the heap so it's in the perfect situation for you to exploit it. There's common techniques out there like heap spraying, things like that. They require that you really understand the allocation patterns in the heap. And as we've shown you, DTRACE can hook any function in the system relatively simply, so it's very easy for you to write a script to understand what the heap's doing for a specific application. So actually, let me go back there. As I said, Immunity Debugger helps you on Win32. One of the really useful tools for Nix-based exploits is Gerardo Ricarte from Core Security's Heap Tracer. So that's an OpenGL visualizer based on LTrace or STrace or Truss for the heap. So there's a lot of different ways we can really understand heap vulnerabilities and write exploits from them using DTRACE. One of the standard things we can do is just look for double free or double mallocs in an application while it's under test, while you're fuzzing it. We can do this without having to load in these funky libraries. I don't know how many of you have tried to write exploits on Solaris or Linux and had to compile your own version of the malloc with debugging information so that it prints out every time a malloc happens. You don't have any of those problems with DTRACE. It's right there for you. The other thing you can do, of course, is heap visualization. So we have directed graphs. We can output to Gerardo Ricarte's heap tracer to get an OpenGL visualization of it. Or we can use Apple's little instrument utility to give us some useful visualization of memory leaks or something like that that may help you in your exploit. So with predicates, you can zoom in to just the functions you're interested in. A lot of the like log malloc, there's a lot of really nice tools on OS X for looking at heap allocations. But again, we're lazy reverse engineers, and there's a lot of, it's very time consuming to grep through these logs looking for a specific instance of one tiny heap allocation or a 1 byte leak. We can do that simply with DTRACE and our retrace toolkit. So you can spot off by 1 errors without a problem. So if you're familiar with the Mac platform prior to 10.5, you know about K-Trace. So my analogy is K-Trace is Bonds on the Pirates, DTRACE is on steroids, it's K-Trace on steroids, so it's Bonds on the Giants. So since generic locations to overwrite function pointers is basically gone, I don't know how many of you are familiar with the paper that Nemo wrote about heap exploitation on the Mac. that was the traditional technique, right? Was to set up a heap allocation pattern so you could overflow all the way to the function pointer for malloc, and then the next malloc would allow you to exploit it. That's done. That's over. So now your really only option for exploiting the heap on the Mac is to overwrite application-specific data on the heap. So that's going to require a very intelligent understanding of the heap allocations for some very complicated applications. So you need me to be your buddy and give you retrace to help you out. As I said, even his technique required a detailed view of heap trace, or of the heap. So quickly, here's a directed graph of the heap allocation sizes. That's no problem for me to generate. I'm going to jump through this quickly since we're running out of time. In OS X, remember, there's actually 4 different heaps per process running. So they break it up depending on how the size of the allocations. So that's something that's very Mac specific that we hope you to understand our retrace heap smash detector. So we keep track of the 4 different heaps for you. We hook all the malloc calls and write them into Ruby hashes. So every time a malloc happens, I'm recording the address of the pointer and the size of that data. And I'm going to use that later to figure out if anybody screwed up. So while we're doing this, every time memory is freed or reallocated, I got to keep track of that. I do that all for you. Again, we hook C functions that then use the heap data. So traditionally, this is difficult, right? You can't use static analysis normally to look at very complicated runtime heap allocation flaws. You just can't see that statically in the code. You have to know what it's doing while it's running. So that would take you a long time in a tool like GDB. What I allow you to do is, since I know every chunk that's been allocated on the heap, if you try to use it with larger data than is available, I know you've overflown. So we check to see if the allocation happens, then we look up in our hash table and say, oh man, you overflowed. So I'm just going to show you a video that will show you what we do. So when an overflow is detected, we know who allocated it. So we know when the malloc happened that was overflown. We know who used it, which function. Did a string copy use it? Did a mem copy use it? Where did that originate? We know how much memory was overflown. We know where the memory is, and we can find out if it's ever freed if we want to do like a write for unlink. So we know a lot just with this tiny script. So I'm going to play this now for you. Where's the lightsaber, Luke? Okay. So here I'm just catting out a simple vulnerable C function, or a little C application I wrote. So if you notice, I'm just mallocing 16 bytes here, and then I'm going to do a string copy to it with 30 bytes, and I'm going to detect this in real time. And I'm also going to, in IDA, I'm going to show you where that happened in your static disassembly. So I'm showing you the basic sizes there. So we're going to go ahead and fire up our heap smasher. So I'm running the crappy program there with obviously an overflown buffer. And I have IDA here running in VMware Fusion. So there's the disassembly for the same C program I showed you. There's the string copy function that's going to overflow. So I'm going to return you there, and I'm going to show you all the tricks I can do here. So this is the IDA Rube program, plugin I'm firing up. So this is a server connected over the network to my OS X. But really, you can use this on your local box. It doesn't matter. You can point it back to localhost. So now I'm just going to fire up my term. I'm going to run my heap smasher with the vulnerable C program, and obviously there's a bunch of A's there that are going to hopefully overflow. String copy. That's the IP. I'm going to fire this guy off. So boom, we detected the heap overflow. We know what address it happened, what probe detected it. If you see there, I found that in the string copy, the end size was 30, but the heap was only 16 bytes allocated. I know the destination, the source address, EIP, and I know the stack frame from where it was allocated from, and I know the destination size and that there. And if you've seen, I automatically made a comment in IDA there, if you can read it. So imagine fuzzing an application while you have the disassembly open and the heap tracer running on the application. It'll go ahead and annotate the disassembly for you so you can look at places that vulnerabilities might have happened, which we think is pretty cool. So again, I'm just going to jump through this, but the heap smasher has all sorts of possibilities for the future. We just have 1 minute here, so we're going to skim through using DTRACE defensively. It's really easy to use this same functionality we've created to do a basic HIDS, a custom HIDS. So you fire off a script to, for example, let's say you have a custom application that you want to protect with DTRACE that's very unobtrusive. You go through, you do some profiling application with some various DTRACE scripts to understand the standard system calls or library calls that are made, and then you figure out which ones that application should never make, and you write a script to notify you. So you have a problem. I want to use QuickTime, but it's got a crap load of holes. Solution, you make a DTRACE script to call stop when weird stuff happens. So QuickTime probably never needs to call binsh and attach to another server. It probably never needs to call mprotect to make the stack unexecutable. So even though HIDs by definition that are signature-based are flawed, this is something that's very simple that you could mock up if you're really worried about a mitigation for a zero-day exploit, and it might help you out. Because of the non-executable stack, there's some pretty simple vectors that you can detect. So here's a quick, couple line HIDs. Basically, we're just going to say anytime QuickTime player launches binsh, you're pwned. So I'll show you this video really quick in closing. Actually, we'll skip the video. Yeah, fast. So last couple things, DTRACE and detecting rootkits. There's a really cool paper written by Arkham at the CCC conference on Solaris for hiding rootkits from DTRACE. DTRACE obviously knows everything that's going on in the kernel, so you have to do some significant work to hide a rootkit from there. We did some basic tests on detecting rootkits with DTRACE, and it's relatively simple to see who's hooking functions in the kernel and that they shouldn't be doing that. Same thing goes for malware analysis. We recently checked out OS X RS Plug A, which was the first Leopard Trojan, and we're seeing, why is my video codec calling, Scootil and adding weird stuff to my DNS? Your codec probably never needs to do that. So in conclusion, DTRACE can collect an unprecedented range of data.
It's very good at giving you a broad view of the application. It's very good at giving you a very specific view of the application. That's exactly what we want to do as reverse engineers. So there's a lot of areas for future work here. We hope we've triggered some of your own ideas about how this can be applied, and we'd love to talk to you about it.
Yeah, one of the cool things is you can even use it for blind SQL injection using MySQL probes and things like that. So check out Retracer, Blogspot. That's where our framework's going to be, and you can get it for free now.
Let's give Tiller and David a round of applause.